Hello everyone. So welcome to the fourth lecture of the module 2, which is the module for nonlinear equations. So in this lecture I am going to introduce you another method for solving nonlinear equations, and the method is called fixed point iteration method. Why we say it fixed point iteration method? Because it is based on the concept of fixed point for a given function. In the past 3 lectures we have learned about bisection method, then regular falsi method and Newton-Raphson method. So in all those methods what we were doing, we are finding the iterations, we were establishing an iterative equations, and based on the iterative equations we are finding a sequence which is going to converge to the root of the equation. In Newton-Raphson method we were calculating the derivative of a function. However, in earlier method like bisection or regular falsi method, we did not calculate the derivative. Since in Newton-Raphson method we were calculating derivatives and we were doing some extra efforts, we were having the assumption that function should be twice differentiable, and hence based on that we were getting a good convergence of Newton-Raphson method compared to the earlier methods. Now let us discuss about this fixed point iteration method. So first of all, what is a fixed point? So the fixed point of a function f of x is a point x such that f of x equals to x. For example, if we have a function f x equals to x square minus x minus 3, then the fixed point of f x are given by f x equals to x, that is x square minus x minus 3 equals to x, and when we solve it we can check that we are having two fixed points for this particular equation, that is one is 3 and another one is minus 1, because if we calculate f of 3, so it is coming out 3 into 3 9 minus 3 minus 3, so 3, and if we calculate f of minus 1 it is coming out minus 1. So in general we can say a function the fixed point of a function is given by the intersection of this function with the line y equals to x. For example, this function is having these two fixed points. If I take another function f x equals to f x equals to sin x, so x equals to 0 is the only fixed point of this function. Similarly, we can get another functions for which we can have one fixed point, two fixed point, or more than two fixed points. For example, if you take the identity function, all the points of this function are the fixed points. Now based on this concept of fixed point, we will develop our fixed point iteration method. So let us say we are having a nonlinear equation f x equals to 0. Now we need to write this function f equals to 0 function f in such a way that I can write it as x equals to gx, in such a way that the fixed point of this particular equation becomes the root of this equation. Means if this is the equation 1, this is the equation 2, so the fixed point of the equation 2 becomes the root of equation 1. So fixed point of 2 is the root of 1. Now, if I give you a nonlinear function f of x, I can write this function in this form in several ways. For example, consider a function f of x equals to x square minus x minus 3 equals to 0. So, here f of x is x square minus x minus 3. So, I can write this function as x equals to x square minus 3. So, here and that is equals to g x. So, here g of x is x square minus 3. Another way of writing this, I can write this x equals to square root of x plus 3, and that is plus minus. So, here g x can be square root of x plus 3 or g x may be minus of square root of x plus 3. So, this is my g x. So, these are the two ways of writing this function f x in terms of x equals to g x. We can have several other ways of writing a function x equals to g x. Now, after writing equation 1 into equation 2, then what we will do from the 2, I will generate an iterative scheme that x of n plus 1 equals to g of x n. If x is a or x star is a fixed point of this particular g, then what will happen when this sequence or this iteration scheme will converge towards the x star? Finally, this will become x star equals to g of x star, and hence x star is a fixed point of this, which gives the root of f x equals to 0. So, this particular formula is called the iterative scheme or formula for the fixed point iteration method. The only thing we need to take care in this, that choice of this function g, how to write this g from the given equation f of x equals to 0. So, criteria to choose this function g should be given in initial x naught, then the iterative scheme of this equation or iterations of this equation gives you can be calculated very easily. The second criteria for choosing g is the sequence x n is convergent using that particular g, and third one is the limit to which sequence x n converges, let us say eta, it should be a fixed point of g x, that is g of eta equals to eta. Now, if we talk about first point, that given an initial value of x naught using this method, we should be able to find out subsequent approximations of x n. If you take a very simple example, let us say f x equals to x square minus x equals to 0. Suppose I need to solve this equation. Now, what will happen if I choose x as minus of square root of x equals to g x, that can I calculate? I take this x in the right hand side and then I can take the square root of the both side. So, it will be plus square root as well as minus square root. Suppose I take this minus square root. So, then my x 1 will become minus square root of x naught. Now, this g x is defined only for positive x or non-negative x. So, if x naught is greater than 0, what will happen? I will be able to find out x1 which will be a negative number. Now, when I will calculate x2, that will be minus square root of a negative number which is my coming from the first iteration. I will not be able to find out x2. Hence, I am not able to find out any subsequent approximation of xn, and hence we should choose gx in such a way that we can find all the approximation in subsequent iterations of xn. Moreover, the convergence of the fixed point iteration method depends on function g, that is how you are choosing your function g, and the initial approximation x naught. Now, I am going to explain few of the assumptions for choosing g, and the first assumption is gx should belong to the domain of x. That is, if x belongs to a closed interval a to b, then gx should belongs to closed interval a and b. Why I am saying this, or why I am taking this assumption, that if we have a x naught between a to b, then for all n, xn should lie in the closed interval a to b, because xn plus 1 equals to g of xn, and hence xn plus 1 should be defined in the closed interval a to b, and it can happen only when your domain of g is between domain of g is between a to b. The another is g should be a continuous function. That is, if the nth approximation of xn tending to x star, then x star can be written as limit n tending to infinity xn, that is equals to limit n tending to infinity g of xn minus 1, since xn equals to g of xn minus 1. Now, since xn minus 1 is a fixed point of g, I can write it, I can take g out and limit n tending to infinity x of n minus 1, and it is equal to g of x star. Now, this is very important assumptions, and this is a condition of the choice of g, which subsequently tells us that whether the method is going to converge for this particular choice of g or not. So, the iterative function g is differentiable on a b. In addition, there exists a constant k between 0 to 1, open interval 0 to 1, such that the absolute value of g prime x should be less than equals to k for all x belongs to a to b, interval a to b. Hence, I can write this condition like this, I can state like this: the absolute value of g prime x for all x belongs to a to b should be less than 1. If you are having such a g, then your fixed point iteration scheme converges for any initial approximation chosen from the interval a to b. Moreover, we are having a condition on the uniqueness of fixed point, that is, assume that g is a continuously differentiable on a closed interval a to b, and the domain of g is in closed interval a to b with lambda, that is the maximum value of g prime x for all x belonging to a to b, and this value is less than 1, then x equals to gx has a unique solution x star in a b, that is the fixed point will be unique in this particular interval a to b. The another one is for any choice of x0 in this interval a to b with xn plus 1 equals to g of xn, n equals to 0, 1, 2, etc. The sequence xn will converge to this unique fixed point. Further, the absolute value of xn minus x star will be less than equals to lambda raised to power n x0 minus x star, because 1 lambda will be added in each iteration. like xn minus x star will be less than equals to xn minus 1 lambda times xn minus 1 minus x star less than equals to lambda square xn minus 2 minus x star and so on, and that will be less than equals to lambda raised to power n upon 1 minus lambda into absolute value of x1 minus x0, and limit and tending to infinity, the error in n plus 1 iteration upon error in nth iteration will be equals to g prime x star. It means when n is quite large, the limiting value of the error in n plus 1 iteration, that is E n plus 1 upon E n, should be less than 1. Because we are taking this x star will be in this interval and we are taking lambda as the maximum value of g prime x for all x in this interval. So, x star will be somewhere in this particular interval, and hence this value will be always less than 1. So, limiting value of this E n plus 1 will be less than E n, strictly less than. After this, let us take few examples which we will solve using this fixed point iteration method. So, consider the equation f x equals to x cube minus 7x plus 2 equals to 0. This equation is having root in 0 to 1, because when we test it at x equals to 0, it is coming out 2, which is a positive number. When I test it at x equals to 1, so f of 1 coming out to be 1 minus 7 plus 2, that is minus 4, which is a negative number. So, here f0 into f1 is a negative number, and according to intermediate value theorem, there will be a root between 0 to 1. We can write this equation as x equals to 1 upon 7 x cube plus 2. So, we will have gx equals to 1 upon 7 x cube plus 2, and you can see the function g belongs to 0 to 1 will be always 0 to 1. So, domain equals to range. It means that whatever domain you are having for x, the same domain I am having for g of x. That is our first assumption in this method. Moreover, if you check g dash x, that will be always less than 3 upon 7 for all values of x between 0 to 1. Thus, by the convergence condition of the fixed point iteration method, the sequence x of n plus 1 equals to 1 upon 7 x n cube plus 2 will converge to a root of x cube minus 7 x plus 2 equals to 0. That is, the fixed point of this equation will give you the root of this equation. The algorithm works like that. Suppose we are having equation f x equals to 0. First, we write the given equation in the form g x equals to x. Then we start with an initial approximation, say x naught, and then we find a successive approximation of x n in different iterations. Now, let us take another example of fixed point iteration method. Suppose we are having an equation that is the fourth order polynomial equals to 0 and polynomial is x4 minus x minus 10. So, consider g of x as 10 upon x3 minus 1. So, by the fixed point method, the iterative formula will become x of n plus 1 equals to 10 upon x n cube minus 1 for n equals to 0, 1, 2. We start with an initial approximation x naught equals to 2, and then x1 will become 1.429, x2 will become 5.214, x3 will become 0.071, x4 will become minus 10.004, x5 will become minus 9.97 into 10 raised to power minus 3, then x6 will become minus 10, x7 will become minus 9.99 into 10 raised to power minus 3, x8 will become minus 10, and then it will always oscillate between minus 9.999 raised into 10 raised to power minus 3 and minus 10, and which shows that the iterative process will never converge. So, what is the problem here? The problem is, if you see your Gx, so here we are choosing Gx as ten upon x cube minus 1. If I find out g prime x, it will become minus 10 into x cube minus 1 raised to power minus 2 into 3 x square. So, basically I can write it minus 30 x upon x 3 minus 1 whole square. Now, if you check that when x is 2, so when x is 2, it will become minus 30 2 upon 7 square, which is minus 30 into 4 upon 49. So, hence g prime, absolute value of g prime 2 will be somewhere 120 upon 49, and which is greater than 1. So, this choice of g does not fulfill the requirement of the convergence, and hence we are getting such a behavior of the iterative scheme that it is not going to converge. If we take another function g for the same equation x 4 minus x minus 10 equals to 0. So, another way of writing g x is x plus 10 raised to power 1 upon 4, then the fixed point iteration formula becomes x n plus 1 equals to x n plus 10 raised to power 1 upon 4. Again, if I start with x naught equals to 2, so my x naught is 2, I got x 1 as 1.861, x 2 at 1.8558, x 3 as 1.85559, x 4 as 1.85558, and then x 5 as 1.85558, which is same up to 5 decimal places in these two iterations, and hence my fixed point iteration method converges to the root with an accuracy of 5 decimal places in just 5 iterations. And this is happening because if you calculate here for this particular choice of Gx, so here I am taking Gx is x plus 10 raised to power 1 upon 4. So, here g prime x will become 1 upon 4 into x plus 10 raised to power 3 by 4. If I calculate g prime 2, it will become 1 upon 4 into 1 upon 12 raised to power 3 by 4, and this number will be less than 1, and hence the condition for the convergence on the choice of g is fulfilled here, and that is why method is converging quite faster. If we take another choice, the third choice of g, that can be written as x plus 10 raised to power half upon x, then the fixed point iteration formula becomes x of n plus 1 equals to x n plus 10 raised to power half upon x n, and here let us start with x naught equals to 1.8, which is quite close to the exact solution. Earlier we were taking 2, but now let us take 1.8. So, here x0 is 1.8, x1 will become 1.9084, x2 will become 1.80825. Continuing in the same manner, we see that the solution converges to 1.8555 in 98 iterations. So, in the earlier method we were taking the initial solution a bit far away from the root, still we are getting the convergence in just 5 iterations. Here we are getting initial solution close to the exact root, but we are getting a solution with a large number of iterations. However, method is converging. Hence, the choice of G because and it is happening because if you find out G 3 prime x at x equals to 1.8, it is just close to 1, means it is near around 0.9 something, and hence we are taking more number of equations. Hence, in this method choice of G is very important for the convergence. You need to check the condition absolute value of G prime x less than equals to 1 for all x belonging to interval a to b for each G, and which is giving the value very less than 1 or smaller one, we will use that one, smaller one as well as less than 1 for further iterations, and based on that we will use our fixed point iteration method. Moreover, this method is quite simple in formulation if we leave out the choice of G. So, thank you very much for this lecture. In the next lecture we will learn about the solution of system of nonlinear equations. Like in module 1 we have solved the system of linear equations, here we will take the system of nonlinear equations. If we take the system of nonlinear equations, we will have nonlinear equations involving more than one variables, and therefore we will modify our Newton-Raphson method as well as fixed point iteration method for solving such type of systems of nonlinear equations. Thank you once again.